I'm Carolyn Russell. I'm Tactical Marketing Manager for Atmel. Atmel is a multi-billion-dollar company. We concentrate a lot on microcontrollers, but we have memories and touch technology. But another aspect of Atmel is that we have a line of rad-hard ICs, and I was going to talk a little bit about those and what we're doing in our company. It's going to be a very broad overview of what we're doing. Page down maybe works better. Great. Okay, so Atmel has been doing space products for over 30 years. We provide parts that are hardened by design. We are very good at taking a commercial technology and library and hardening the libraries and making changes so that we can have good radiation effects, good radiation effects. We have rad-hard ASICs, rad-hard SRAM-based FPGAs, rad-hard microcontrollers, processors, and memories. We manufacture per the latest military specs, and our parts are QML qualified. Thank you. So a lot of our parts, I thought that you're going to the moon, you want to know a little bit about the radiation effects of our parts. Most of our parts, at least the most recent parts, most of them have been tested up to 300K rad. Our single event latch up performance has an LET of typically greater than 70 MeV, sometimes as high as 95 MeV. And the SEU, of course, is also dependent on the device. But some of the examples I have is we have a 180 nanometer ASIC technology called ATC18RHA, and that has an SU of 4 × 10⁻11 errors per bit per day. Our rad-hard FPGA, the ATF280F, has no SEU up to 30 MeV, and our Spark processor, the AT697F, has an SEU better than see what happens. Has a SEU better than 32 MeV. And of course, we have radiation reports for all of our parts, so if you want to look at the data, that is available also. We have lots of flight history. In our ASICs, this is just a small example of the various missions that our parts are flying on or will be flying on. Same thing for our FPGAs. We're starting to see a little bit of flight history for these parts also. Whether it's a 3D camera or it's usually some experiment on any of these programs at this point. Our Spark version 8 processors, lots of technology, lots of flight heritage. This is just a small example. Whether we're on our way to Jupiter, or we're on the Prova 5 mission and we're in control of the aptitude and orbit control systems on that ship. Or we're going around the sun, we're going onto the moon, or possibly onto Mars. The ASIC roadmap, just again, a very big overview. We're still producing parts that are in 35 nanometer technology. We have 180 nanometer technology. Again, we have hardened these libraries. So we've taken a commercial library, we harden it so that it's available for the space community. The 180 nanometer is flying now. The 150 nanometer, this is relatively new. We're basing this off of an automotive technology that Atmel uses. And we're using and targeting our automotive because automotive has longevity. which we need in the space community. So by targeting Atmel's commercial or automotive technologies, hardening the libraries, we give longevity to the space community. The 150 nanometer technology is an SOI technology. It is a mixed signal technology, which will allow us to do more analog devices in our ASICs. And then we're working on a 65 nanometer CMOS technology. I don't touch it. I don't touch it, honest. Okay, all right. So that's a little bit overview of the ASIC roadmap. An FPGA roadmap is we have what we call an AT40K family. It's, again, an SRAM-based FPGA. We have hardened the FPGA. We've hardened the flip-flops, the memories, the clock, the resets, every part of that particular device. The AT40K is the current family. We're going to get up to around 900K ASIC gates. And then we're going to move to a new technology and a new architecture, which will allow us to get into the 2.5 million plus gate FPGAs running at a closer to like a 300 megahertz speed. That's off in like the 2016 timeframe, but we are starting to fly the current devices, which are the APF280 and the 450 will be available next year. Memories, we're concentrating on SRAMs and E2PROMs. The E2PROMs because you need a configuration IC for our FPGAs. So we're working on that. We've just recently released a 4 megabit E2PROM. The SRAMs, we have 4 megabit and 16 megabit. We also have some 1 megabit SRAMs, and we're working on a 40 megabit SRAM currently. Processors. Right now, this big circle in blue, that's a Spark version 8. It's based on a Leon 2 processor. We have several parts available now. We have one that runs at 100 megahertz. We have one that runs at 50 megahertz. And we have another one that has combined the processor with an FPGA into one package so you can have some reconfigurability. All of these are running at 300, have been tested up to 300K rad. Plus an SEL greater than 70 MeV. The next generation will be using our 65 nanometer technology. Atmel hasn't decided what architecture we're going to use for our next generation. We're looking for input on that. Now, we are a microcontroller company, and we do two different microcontrollers. We have an AVR, that's an 8-bit microcontroller, and we are also very good in ARM. We're looking at ARM. We've had some very positive reactions to that, but we're always interested in your reactions and what kind of processors you'd like in the next generation also. This will allow us to get into the 500 megahertz processors, go into the dual cores, and so that this is, concept stage still, but we're definitely looking at it because we are developing the libraries for that 65 nanometer technology, which we have access to. But what I'd like to talk to you guys a little more detail about is microcontrollers. And, there's no standalone 8-bit microcontroller for space out there. Most of you, if you need it, you're taking a core, you're putting in an FPGA, and you're flying it that way. And you're dealing with the high power consumption FPGA, maybe some limitations to the speed of the device, and certainly the radiation effects of your FPGA. So what Atmel has done, or we're doing, is AVR is an 8-bit microcontroller. It is a proprietary Atmel technology, and we're moving to see if we can give you a low rad hard version of that. So this is kind of our commercial portfolio for microcontrollers and processors. We have the 8-bit AVR, we have 32-bit AVR and ARM, and then we have also some ARM microprocessors. And we're going to take that and The advantage of this is that they're easy to use. They have single cycle performance, and the tools are available. Those tools are free of charge. You can start your development in a commercial part and then move it possibly to the low rad hard version that we're offering for space. We're going to take also the knowledge and the skills we have in automotive qualification, the skills and knowledge we have of qualifying space parts, not only doing the low rad hard parts, but then also moving into avionics also, and using our knowledge of both the space and the automotive so that we can also offer some avionics type parts. The low rad hard part, we're looking at AVR. Actually, we're taking an AVR part. We're taking an automotive Mega 644. We've taken the design. We are changing some of the mask layers, especially the epi layer, to increase the SEL, single event latch up. And we're building a new part. It'll be we're starting with the 8-bit microcontroller. We expect it to have a 470 total dose of 50K rad, the SEL greater than 70 MeV. The SEU and SET is really going to be about 5 MeV, and we don't expect much better than that because we're still working. It's not radiation hardened by design. We're using a commercial design and a commercial library. We're going to put in a small hermetic package. We're going to do the testing, that QML type testing, so that you have parts that are for flight that are in the QML-Q or QML-V levels, so that we're doing the die inspection, the burn-in, the record, the 3-temp testing. We're hoping to get -55 to 125, normal military temp range. You have all the tools and the evaluation kits that are available from the commercial side. So they're free tools. The evaluation kits for the commercial parts are certainly inexpensive, and it's an easy step from commercial to a rad hard. The first part is expected. We'll have engineering models beginning of next year. We'll see how this goes. We'll probably do the same thing for an ARM part, and if all things go well conceptually, then we'll take an AVR. We'll use one of our technologies that we've hardened the libraries for a mixed signal and do a rad hard microcontroller. So what we're going to do and what we plan on doing is Atmel is going to continue our commitment to develop rad hard designs and provide QML qualified devices. We're going to continue to harden libraries and other newer technologies to provide faster parts and lower power consumption parts. We're going to continue to develop and provide faster development times with SRAM-based FPGAs. We're going to address the lower cost solutions with high-rail microcontrollers for the space and avionics markets. We're going to use Atmel's system-on-a-chip expertise and our IP portfolio so we can extend those offerings to our space and avionics product lines. And we're going to take the benefits of having automotive technologies and use those technologies to ensure longevity for the space community. Thank you.
Thank you. Any questions?